Lesson 5. Managing and Logging Errors. In this lesson, we will cover error testing, local and global error handling, and error logging. Error testing is a mechanism of testing your code to see how your system responds to errors. It is important to identify areas where errors are most likely to occur and determine how the system should respond to them. Error handling should occur in two stages. In development, error handling should be noticeable and clearly indicate where errors occur. This is useful to help determine where bugs are in your VIs. However, in deployment, error handling should be unobtrusive and provide clear prompts to the user. Test your code by forcing errors and making intentional user errors. You can force errors by injecting an error cluster on the error wire at locations that an error may occur at runtime. You should also identify where errors may be injected by a user, such as canceling a file dialog, specifying an invalid file, or providing invalid or out-of-range values. When forcing these errors, you should have some expected behavior that the system performs. Common behaviors on error are to shut down gracefully or recover from a non-critical fault. It is important to verify that your system has a catch-all behavior in the event that an unexpected error occurs at runtime. Local error handling is a mechanism for handling errors in a sub-VI or subsystem. It should be the primary approach for handling minor errors that can be prevented or controlled and don't interrupt normal execution. These kinds of errors are usually predicted, and there is some action that can be taken to resolve them immediately. For example, if a file becomes too large, you can create a new file and update the refnum. Local error handling should generally be preventative. You should determine possible sources of an error and develop code in such a way that errors cannot occur. Once an error has been handled locally, it is important to clear the error from the error wire. Global error handling provides a mechanism for your code to handle unexpected errors at runtime. It is generally more robust than local error handling and designed not to handle specific errors, but instead as a catch-all for unexpected errors that occur at runtime. Global error handling is typically performed by the top-level VI in an application or a separate error handling module. It provides a way for the application to shut down safely in the event of an unexpected error. Custom error codes allow you to generate your own error messages. Error codes for custom error messages are defined in the ranges shown. It is vitally important that these errors are well documented, as they are unique to your application and not supported by national instruments. To define a custom error code, you can use an error cluster, an error ring, or the general error handler VI. For multiple applications using the same error code, you can use the error code file editor. This tool creates XML files that contain all of the information for the errors. Error handling in the queued message handler. The error handling in the queued message handler template project takes place at the end of each message handling loop iteration. If the case structure exits with an error on the error wire, it is handled inside of the general error handler VI. This error handler is fairly simple and contains a static list of errors to ignore, as well as errors that may be ignored at runtime. There's also a flag to enqueue the exit message rather than the error message. Looking at the check loop error VI, we can see that the exit on error decides to send either the exit message or the error message and enqueue it as either a priority or normal message. This enqueues a new state to the queued message handler. The queued message handler is then sent to either the exit case or the error case. In the error case, the error is displayed to the user and any error handling code is processed here. If the flag to send the exit case is sent, the message handling loop instead executes the exit case. In the exit case, the message is still displayed to the user, but the shutdown procedure completes as normal as well. Global Error Handler VIs can be built into a sub-VI to handle specific errors from multiple locations. This is a common practice for when the same error may occur from multiple locations. If an error can occur from only one VI, it's best to handle it locally.
In the sprint planning meeting for this iteration, the product owner chose to implement 2 user stories that describe error behavior. Critical errors require shutting down the application because they cannot be otherwise managed. If they are not handled, critical errors may result in injury to personnel or damage to equipment. They may also place the system into an unmanageable state. Non-critical errors are more akin to inconveniences that should not prevent continued execution of the application. After discussing the user stories with the team, you identify and classify several errors that the code must handle. This flowchart shows how the application should handle a critical error. Regardless of where the error occurs, it should be propagated up to the message handling loop. Once you get to the message handling loop initiate stop block, functionally it is exactly the same as if you'd clicked the emergency stop button. Now let's look at the functionality that you're going to implement in this exercise. When I run main VI, I'm prompted to select an INI file. Before, if I'd canceled this dialog, an error would have been generated and we would shut down the application. But now, we treat this as a non-critical error, and instead of shutting down the application, we just load a default INI file. Another error that we handle as part of this exercise is if I select an invalid file when I'm supposed to select my INI file. So for example, if I go to All Files and say select the LabVIEW project instead of the INI file, we generate a critical error and the application shuts down. In this exercise, you will modify your code so that it can handle both types of errors. Let's take a look at the solution to exercise 5.1. When we open main VI and look at its block diagram, there are a couple of different places in this VI where we can predict the possibility of an error occurring. First, let's look inside a boiler system open. And from here, let's look at read configuration data. The first possible error that we're going to handle is what happens if the user cancels the file dialog VI. In that dialog, they're supposed to select an INI file, and that's where we're going to read our values from to initialize our user interface. If they cancel that dialog before, what we would do is we would just generate an error and shut down the application. Because that isn't really a critical error, what we'll do now is instead of closing down the application, we'll just load a separate default INI file, boiler.init.ini, and read values from it. The second possible error that we're going to handle within this VI is what happens if the user selected a file but it isn't a valid INI file. To handle that, we'll go into read UI constants, and we see that within this VI, we attempt to read values for fuel control valve maximum and minimum. If either of these reads is unable to locate that value, then we go to this case where we generate custom error 5000, indicating that we were not able to read the UI constants from the INI file. The next possible error that we're going to handle is what happens if we receive an invalid message within the message handling loop or the boiler controller. Say, for example, in the reset case here in our event handling loop, instead of sending a reset message, we send a resets message. When we look at the case structure for our message handling loop, we see that we do not handle a resets message. So instead we'll go down to the default case. Here we generate custom error 5003, indicating that an invalid message string was read. If we look at boiler controller, we do something very similar. When we look at the default case here, we see that we're generating custom error 5004, indicating that an invalid message was received. Note that we're using a different custom error number here. The reason we do that is to differentiate error messages that we're generating from the boiler controller loop versus the message handling loop. So what happens if somewhere else within our application We just have some error that we generate, and it gets passed on to the shift register and read into the DQ function. Here, if an error occurs, first we have the option of clearing that error. So we can specify any errors within this case that we want to just clear the error and move on with normal dequeuing of the message. However, if an error is passed in and it's not an error that we want to clear, then instead of a normal dequeue, we'll go to the false case and go directly to the error case for that loop. Now before this we were going to the exit case. We've changed that so we're going to go to the error case instead so that we can handle whatever error it is in our own way. When we look at the error case for the message handling loop, we see that we just initiate the stop. Within the boiler controller, if we receive an error, then we're going to send an error up to the message handling loop, which will execute that error case and then initiate the stop functionality. For this application, when we go to the initiate stop case of the message handling loop, it's exactly as if we'd clicked on the emergency stop button for our application. The queued message handler template has a built-in global response for critical errors. Errors detected by the DQ element VI are treated as critical errors, sending the message handling loop straight to the exit case. In this exercise, we change this default behavior to send the message handling loop to the error case instead of the exit case, so that we can implement our own shutdown process after an error occurs.
Logging errors can be a useful tool for debugging your application. It is a good way to gather information about what errors have occurred without being obtrusive to your user. In addition to logging the error that occurred, it's useful to log the source the error occurred from and the time that the error occurred. Take a few minutes to explore this example of an error logging VI.
In the sprint planning meeting for this iteration, the product owner chose to implement a user story that describes error logging behavior. As it is currently In the sprint planning meeting for this iteration, the product owner chose to implement a user story that describes error logging behavior. As it is currently implemented, critical errors cause the application to shut down without providing any additional information to the end user. To implement this user story, your team identifies several development tasks. You will add the log error functionality so that it executes between the MHL error and the MHL initiate stop messages. Now let's take a look at the error logging functionality that you're going to implement as part of this exercise. When we run main VI, we're prompted to select our INI file. If I were to choose some other file type, such as boilercontroller.lvproj, we get a dialog indicating that a critical error has occurred and that I should check errorlog.txt for more information. So I click OK, and then I click OK for my pop-up just that lets me know that I reached the initialize case, and then our application shuts down. That's because this was in fact a critical error which we should shut down the application for. But we also now have an errorlog.txt file in my root project folder. So I'll open this, and here I get my message indicating the time at which the error occurred, what error code number, and then what was the error, indicating here that it was not able to read UI constants from the file that I selected as an INI file. So I'm going to close this, and now we'll take a look at another type of error that we can log. So here I'll select a correct INI file, and now when I click the reset button, another critical error occurred. So I'll go check the errorlog.txt, and you can see that we're appending to the end of this log file a new message indicating that error 5003 occurred, and here it's indicating that an invalid message string was sent to the message handling loop. When I take a look at the block diagram, I can see that, aha, in the reset case, instead of sending a reset message, I sent resets. So I can fix this, and now my application will run properly. In this exercise, you will modify the application to log data about any error that causes the system to shut down. Now let's take a look at the solution to exercise 5.2. When I open main VI and we look at the block diagram, I'm going to go over to the error case of the message handling loop. When we receive an error message, we also pass along with it data indicating what error occurred by passing the error cluster from the time of the error. From that error cluster, we want to extract the error code and the error source. We're going to log that information to the file. Now for the file that we're creating, we're going to create it relative to the location of our current VI. And then we're going to name the file errorlog.txt. If the file exists, then we're going to open the existing file. If it doesn't exist, then we're going to create a new file. Now for the file open operation, you note that we clear the errors. The reason we do that is that even if there's a problem opening that file or creating that file, we still want to go into log error VI. We're using the error cluster primarily for data flow. We do not want any errors to prevent the log error function from running. So let's take a look now at what happens inside of log error. So when we're going to log, first we build our string for what data we're going to log, and that string is going to include the date, time, and seconds, so when did the error occur. We're also going to pass along the error code and the error source. Now, as part of the logging operation, we're going to check to see if the error file that we attempted to create in our error case, was that a valid file. Now that's where we handle the situation that some error occurred in the file open. If an error occurred, then instead of attempting to log to the file, we're just going to display the error string that we created earlier. We're just going to display that within a one-button dialog. If there was no error and we ended up with a valid file reference, then we're going to take the file, write to the end of it, and then write the string data that we generated earlier. We're also going to have a one-button dialog just to indicate that a critical error occurred and that the user should check the text file for additional information. Now let's go back to our error case. Within our error case, if there was not a valid file, then we're done. We displayed our one-button dialog, everything's set. However, if we did generate a valid file, then we need to close that file reference before we move on. It's important to note that this is only one possible way to handle logging critical errors to disk. You might wonder, how else could I handle the situation where an error is caused by attempting to write error information to a read-only log? One approach would be to create a new log file if the specified one is not writable. You could also prompt the user to specify a different log file. A third option would be to prompt the user to make the file writable.
You have completed this lesson. Here's a summary of what we covered.